Hi, and welcome back to the course Electrical Systems in Agricultural and Biosystems Engineering. This is lecture number 9, and we're going to talk about the transmission systems. We are done with the power generation part, and immediately after it is the transmission, because we want to distribute or to transmit the energy or the power in the form of electricity to where the electricity is needed or where the power is needed. Let's start with a table showing the three key divisions of the electricity industry, where we have generation, transmission, and then distribution. Transmission and distribution are both concerned with the delivery of electricity from where it is generated to where it is consumed. Again, because of the great distance and the difference in the requirements. Okay. Now, when I say requirements of the area. Okay. Now, transmission and distribution differs in that the former or transmission carries loads that are significantly or multiple times greater in voltage value than that of in the distribution side. Again, with AC, electricity can be carried in or through or via very long distances, and this is achieved, okay, in the processes that happens via the transmission. So in between generation and transmission, and in between transmission and distribution, what happens is after generation, the voltage is stepped up so that the electricity can be carried by transmission lines over very long distances with the least voltage drop possible. Now, that voltage, okay, very high voltage, around thousands of volts, the voltage indeed will be minimized with losses, but it is rendered unusable by the appliances. So in between transmission and distribution, the electricity needs to be stepped down so that the voltage value will now be at a level that is readily usable by equipment in the homes, in commercial areas, and even in industries. Okay, so that's the difference between the two. And the distribution side will be carrying the delivery of the power from the substation. So in between generation and transmission, there is a power station, and in between transmission and distribution is a substation. Therein lies the magic of the AC electricity system. We have transformers that step up or step down the electricity, and that's the main topic of this lecture, of this set, the two sets of the two lectures. Okay. Now, while the power generation and transmission and distribution cycle or process or setup is true for most of the time, okay, from where the energy is generated to where it is used. There are specific or special cases where we have independent power producers or non-utility generators. That's why you have here a separation between the two. Now, in an IPP or NUG, okay, the energy in the form of electricity is produced and consumed, okay, by uh, a specific uh, a producer and conductor. It could be the producer itself that is producing, consuming the energy. It could be involved in an industry such as steel, steel production. Okay, it could be in other industries that are highly energy intensive. There are also cases where you have the generators producing electricity and supplying directly to industry consumers. But surely these uh, are specific, okay, to the industry and not to commercial and industrial, the commercial and residential sectors. Okay, so for both the commercial and residential, they will have to pass through the transmission and distribution sides. Now, in the Philippines, the transmission, okay, we have a lot of plants producing energy or electricity, and they're scattered across the Philippines, and then they are connected to the grid. In the current setup, okay, the Luzon grid is connected to the Visayas grid, but not entirely the entire Luzon. Okay, so the main Luzon grid is connected to the Visayas grid across a cable across the I think it's between Samar and Sorsogon. I'm not sure. I have to make sure. Okay, but the idea is to connect them, to interconnect them, so that there is a um, collection of supply. So they are are supplying for the whole area instead of just two distinct or separate areas. Now the transmission is consigned by the Transco. Okay, this is the government-owned corporation. So the Transco consigned the transmission of electricity to the National Grid Corporation of the Philippines. Okay, now the distribution side, they are now involved with the uh, distribution of electricity to consumers, particularly to commercial and residential customers, and also some industrial plants and operations. Again, the electricity that is produced by a power plant is consumed when it is produced. Okay, as far as generation is concerned, it is almost always located far from where the electricity is required or needed, and we just have very classic examples of them with the power plants that we have in the Philippines, like the Tiwi geothermal plant in Albay and the Macban, or the Makiling Banahaw power plant in in between Laguna and Batangas. So these are two geothermal power plants that are located far from the electricity consumers. Okay, in fact, they are in remote places or remote barangays of these provinces. Now, now this is the importance of transmission and distribution. This is where transmission comes in, because we want to deliver. Okay? We want to deliver electricity that is reliable and cheap, and this can only be accomplished by connecting power stations to substations, and to interconnect the load areas together. Okay, that would be the generating stations and individual systems. And then we want to interconnect utilities. Now, this is where we introduce the concept of stepping up and stepping down the voltage via the transformer. Okay. Here is our transformer. We have 3 transformers supplied in across the diagram. Okay, this is a typical generation, transmission, and distribution diagram. Okay, and to minimize the greatest amounts of losses. Okay, which is which happens. Okay, when we have very long wires. So if we have very long distances of wires, what we can do is to increase or amp up the voltage so that, or step up the voltage, thus to lower the current. Okay, we are particularly sending the same amount of power, but in different properties. One that is very high in voltage and one that is very low in current. And with that, we are reducing the losses. Okay, the voltage drop across wires that is causing the the losses. Okay, because again, voltage is the potential difference between 2 points in a system. So if you step that up, the voltage value that is very high, the difference would be very small. Okay, the delta, okay, the change in the voltage in between 2 points at very long distances will be very small. So again, this is the diagram that we are going to look into, and we are going to particularly discuss the transmission of electricity with the systems that are in place right now. Okay, so again, okay, let's talk about the power transmission losses. And here is a very good example or computation. So we see here that the V, okay, is, or the delta V is particularly, or is equal to IR. Okay, it's merely the current and the wire resistance, okay, which is in terms of heat, okay, it's released as heat. Now the P loss is thus equal to what? I squared R. And if you're going to determine the value of the P loss, okay, and it's shown in table 2 as the line loss, okay, this is for the same wiring, but the wiring is carrying a different voltage amount, the same power, thus the current would be smaller, and the line loss would then be what? I squared R. Okay, so multiplying, okay, your I squared R, that would mean a line loss of, for a 7,200 voltage, 2,304 of the R, while when it's 690,000 volts, it's 0.25 R. You can see the factor in the reduction of the R. So if it is lost as heat, okay, a very high voltage would yield a very small amount of heat loss or line loss via heating. Now we have here a sample of an aerial view of what was shown in figure number 1. Okay, this is actually the same implementation, just in aerial view. You have generating power plants transmitting the high or extra high voltage over here. Okay, and well, they will have to be transmitted. Okay, the high or extra high uh, by high voltage electricity will be transmitted through transmission lines. Well, these are made of metal. They're conductors, and they have to be hoisted by towers across the landscape. And this is what we see um, in uh, in in our landscapes. Okay, the very big transmission towers. Okay, or pylons. Now, the plants do not produce electricity at this voltages actually. Okay. Now, that pitch that the transmission lines are carrying. So, a step-up transformer, okay, step transformer would have to increase this voltage by a multiple of thousands. Going back to the towers and the high tension wire cables, okay, it can be seen across our landscapes, and the high or extra high voltage electricity reach the substation where the electricity is then needed, okay, substations, and finally distributed to the consumers after stepping down the electricity. Now, to ensure reliability of a power system, nearby subsystems are interconnected. Okay, they are interconnected. Okay, you can see they are interconnected so that if there's a line, okay, a cut of line over here, there's another line to supply this another substation. Okay, this actually allows alternative sources of electricity should that one line fail or other lines fail. So in reality, a power system will consist of power generators connected together via these transmission lines to form the grid of a power region. Okay. Now, should two systems with different AC properties be connected together, the high voltage direct current or HVDC transmission lines will be used, although merely to connect the power regions with different operating parameters. Okay, let's take a look at the transformer, the heart and soul of an AC electrical system. This is the working element of stepping up and stepping down of the voltage, and the relationship of the two inductors of that's inside a transformer. This is depicted in figure number 4. So we see here an AC voltage source, and that is connected to a primary winding, and that primary winding produces a magnetic force. Okay, and that this magnetic force is received by a secondary coil that is then connected to the load, and that is making use of the induced voltage. Okay. Now, the relationship between the coils that directs the value of the voltage that is being stepped down or stepped up. Okay, take note of equation number 1, where we see the relationship of this figure number 4. Okay, the V primary divided by the V secondary equals the N primary over the N secondary. We can see that using the equation, you can see that the number of coils is directly proportional to the voltage induced, okay, from the primary to the secondary coil. Now, if the voltage needs to be stepped up or increased by a certain factor, the secondary coil should have more coils than the primary coil. Of course, the number has to be determined to come up with the desired voltage value. Conversely, if the voltage needs to be stepped down, the primary coil should have more coils. Okay, so if it's a step-up transformer, the primary coil has fewer turns, okay, of coil. And conversely, it's the other way around for step-down transformers. Another important relationship in a in a transformer is the power in the primary circuit, okay, and the secondary circuit, okay, are the same. Okay, this just follows the conservation of energy. So what happens is, if you have a reduction in the voltage, or an increase in the voltage by multiples, so the I, okay, would be, it's either reduced or increased as well. Okay, so substituting equation 1 into equation 2 leads to equation 3, which is the relationship now of the current in the circuit of a transformer, okay, from the primary and to the secondary coils. Okay. Okay, so that would be all for the transmission side. We're going to talk about distribution in the next chapter, or the next lecture. I'll be seeing you by then.